Good afternoon. Thanks for the introduction. So today I'm going to talk about a specific topic in computer vision. It's called zero-shot learning. So what I do is that I will give, basically I divide my talk into two parts. The first part is to give a general introduction to the background of the problem. So I'll talk about what is zero-shot learning and why I want to do zero-shot learning. And I will focus on a specific technique, which is called attribute learning, which is one approach to zero-shot learning, which has become very popular in the past 3 to 4 years. And then I will talk about the recent work done in our group, which is to look at the limitations of existing zero-shot learning based on attributes, and we propose a particular technique to address those limitations. And in the end, I will present some experiments. So the first part is to introduce the recent work on attribute learning. This part of the slides is based on Christopher Lampard's slides. He gave a tutorial from years ago on attribute learning. These are the number of references you probably want to look at. Okay, so before we talk about zero-shot learning, we want to motivate why I want to do that. The general background is that computer vision research has been studied for over 50 years now. The recent trend is that people have been moving towards large-scale learning. So why I want to do large-scale learning? Basically, even 5 to 10 years ago, when you look at the computer vision researchers, people look at the number of basic problems like object recognition, and people still look at 20 classes for object detection or 200 classes for object classification. So it's pretty small scale. But if you look at the human's ability, because computer vision fundamentally try to reproduce the ability of vision for humans. And human can recognize over 30,000 basic categories of objects. And this is based on some psychological and psychophysical study. And people can recognize many more subordinate ones. For example, people can recognize a forward focus. People can also recognize a forward focus with a stick on the back, saying that a little princess on board. Yeah, you can randomly combine different things together and to generate some new categories. So in fact, people can recognize much more than 30,000 categories. So if you compare 200 categories, the computer vision researchers have been looking at 5 years ago, to 30,000 categories. Obviously, there's a big gap, which means the computer vision algorithm people developed 5 years ago are not suitable for actual applications where you want to give a computer vision algorithm any images out of these 30,000 categories and ask the computer vision algorithm to recognize. It won't be able to do it. Yeah. Another thing is that we found out for a long time that human has the ability to so-called learning to learn, which means a lot of the categories people probably have never seen any images of them. But if people have been familiar with, let's say, 1,000 categories, then you just describe to them what does this particular category look like. Then people have no difficulties in recognizing this new category. So they can actually recognize our object category without seeing any example. So, which means there's some general knowledge about what object look like or what typically they should have has been condensed into some knowledge which can be used to recognize new categories. Yeah? So that's the motivation for us to do large-scale learning. But looking at the conventional computer vision techniques for recognition, now we see some limitations. Basically, the conventional techniques are based on supervised learning, which means if you want to recognize 100 categories, you have to collect hundreds of images, at least for each category. Then you give to a computer vision modules to extract the features, then feed the features into a classifier. Then the classifier will tell you, giving an unknown images, which class it belongs to. That's the standard pipeline for the conventional supervised learning. But if we want to recognize 30,000 classes, and each class we need hundreds of examples, which means we need millions of images collected and labeled into different categories. So that's actually not easy to realize. Even though in the past 5 to 10 years, because of the social media, we have Flickrs, we have YouTube. So we have virtually unlimited amount of data. But the problem is that lots of the images, most of the images, belongs to certain categories. For example, dog, bus, and a car. That's the object people are familiar with. So people tend to take picture of this object and upload to Flickr. So if you look at Flickr, lots of the images belongs to a small group of classes. And the other classes, like this alpaca, is very rare, and not many people actually think this before, so they do not upload those images and they do not label them, which means collect hundreds of images of these categories actually is difficult. So that's the problem with the conventional transfer learning technique. That's why we still not able to extend the computer vision algorithms to handle over 30,000 categories. Okay, but we know that human can actually generalize from the categories humans have seen before to unseen categories. So then people have this concept of zero-shot learning. What does it mean? That you could recognize new class with zero-shot, which means you haven't seen any example of this new class. You can actually aim to recognize it. So this particular research direction is called zero-shot learning, which means the recognition of novel classes without any training examples. So this idea of zero-shot learning follow the concept of learning to learn has been a very hot topic in the past few years. These are a few key references. In order to understand this concept and compare the conventional supervised learning approach to this new zero-shot learning approach, we can look at specific examples. For example, I give you 4 images, all of them contain animals. So I want to ask you, which of these images show a alpaca? Do you know which one? Ask that.
Second one.
This one? We know it's a pretty odd animal, probably lived in South America somewhere, and there are a couple of other animals look similar to this, and this is one particular type. I assume very few people actually see a live one in the countryside or even in London Zoo. So how can we recognize this particular animal classes? In the conventional approach, what we do is that I give you some training images and I label them according to what animal is contained in those images. And you can see that out of the 4 training images, you actually have 2 examples of this particular type of animal. Of course, this particular example of alpaca looks different from these 2, but they are similar enough for you to basically learn a model of what alpaca looks like, and you can use this model to recognize, giving a unseen image. So that's the conventional pipeline. But the problem, as I said before, is that it's difficult actually to collect image of this particular class. And so it's difficult to learn a classifier for that. So what can we do? What happens if that you do not have any training image for alpaca, but you have a lot of image of other things, other more common things, like a cat, mole, dog, and whale? Can we learn something from these categories and use this knowledge we learn from them to recognize alpaca? We know that human can. The question is that can we develop a computer vision model which can do the same thing as human to perform zero-shot learning? So how can we do this? The idea is that we want to learn something from these known categories where we have plenty of training examples. And we want to extract some knowledge about animal, basically. And this knowledge are shared across different categories, no matter what kind of animal they are. Yeah? We know that some animals are living in sea, some animals living on grassland, some animals have 4 legs, some animals do not have any legs. So those kind of knowledge is very useful for you to transfer because they are shared across different categories. Yeah, if any knowledge you want to transfer, they must be shared. So the idea of transfer learning for zero shot is that if we can learn some shared knowledge out of the data we have plenty of training samples for, and we want to transfer this to some new categories where we do not have any training sample to recognize them. So, okay, so let's come back to the problem we want to address. This time we have another object category. It's called, I don't even know how to pronounce this. I'm sure nobody in this room has ever seen this before. But the same question, I give you 4 images. I ask you which image contains this particular, does anyone know? The answer is this one. So it's a fish, yeah? But the name doesn't, suggest anything. What it could be anything, right? So this is the correct answer. Yeah, actually, all these other 3 animals are also pretty rare. We know this is kind of some sort of monkey. Yeah. That's all. What is that? Is a cat or? Anyway, so how do humans recognize this without seeing any example? If I tell you this particular animal lives in water, are white, and have no fur, that's enough knowledge for you to recognize, right? Live in water, this guy and this guy live in water, right? We immediately eliminate these 2, right? Are white, this guy and this guy are white, these 2 are not. So we eliminate this guy. So these 2 descriptions, we call it attribute, are basically some characteristic of this class, are already sufficient for us to recognize this particular type of animal as this image. Yeah, and the 3rd one is that it has no long fur. So apparently this one has long fur, although it's white, but it doesn't live in water. So this one should be eliminated as well. Yeah. So this is the idea behind humans' ability to recognize object categories with zero shot. Because somebody else have seen this animal before, somebody else have written something, some description about this animal. If you just read this article, you know that what this animal looks like. And you know what is living in water, what kind of animal living in water. You know that what are white look like. And you know what kind of appearance correspond to no fur. Now combine this knowledge together, a description and an understanding of each of these description attributes. Human is able to recognize new categories. Yeah? So after we understand this, we could easily, simulate the same ability of human, and which we call it zero-shot learning. The problem is that if we have some attributes to describe each animal classes, but you give these labels to computer vision algorithm, it doesn't mean anything. Yeah, whether it's white or water, it doesn't mean anything. The computer vision algorithm still need to understand what does white and water mean. Let's say white and water, basically you give it to a computer algorithm, it will basically treat the same as X, Y, Z. It doesn't make any sense to a computer vision algorithm. What you want to do first is to understand what is the attribute called white, what is the attribute called living in water, right? Let's say I tell you this animal has property X, has property Y, do not have property Z. And I ask you to recognize this. There's no chance because we don't know what X, Y, Z mean for human, right? But if I give you some examples of these 4 different animal categories. And I told you, dogs have property Y, but not X, not Z. Persian cat have property Y, Z, X, and polar bear X, Y, Z, and the worse have property X, but not Y and Z. Can you guess what does Y, X, and Z correspond to? Yeah? So now we have some proofs. By looking at some images we have, and we know we have examples, and some descriptions, we could actually learn a model about what is X, what is Y, and what is Z. Yeah? So if you look at these four animals, who has X?
Walrus.
So basically polar bear and worse. Yeah? So these two have something in common which are not contained in these two. Yeah? So what do these two animals have in common?
Water.
They all live in water, right? And these two do not live in water. Yeah? So if you have a lot of examples with this type of description, you could basically figure out what does X mean, which corresponds to living in water. Right? So that's the general idea. Basically, if we give a description for this particular animal, for X, Y, but now Z, and we already have a model, what X mean, what Y mean, and what Z mean, which means giving a new image, I can predict whether this image has X, has Y, or has Z. So using this model, I can see that this image has no X, has Y, has Z, and this image has X, Y, but not Z. And I also have a description of this new category, which tell me that this particular animal should have X, should have Y, and shouldn't have Z. And I look at these four images, I look at the description I predicted, and I compare with my description generated by human knowledge, I can make the final decision. Right? So this is basically the idea of attribute-based zero-shot learning. So how can I do zero-shot? I have plenty of training image, and each training image, I know the class label, but more importantly, I know a list of attributes. I know that this class has this attribute, hasn't got that attribute. Yeah? Using this training image, I can learn an attribute classifier, which can be used to predict for a new image whether this new image has this attribute or hasn't got the attributes. Yeah? That's one thing. The second thing is that I have got from somewhere, let's say Wikipedia or some expert in animal, who have told me that this new category should have this attribute and shouldn't have that attribute. So I match these two. Giving me a new image, I predict what attribute it has, and I compare with my so-called prototype, which generated by some human knowledge. And I compare these two. And if they are very similar, I say that this belongs to these new classes. So this is the idea behind attribute-based zero-shot learning. So in this way, a computer vision algorithm could recognize this animal, provided we have a whole bunch of training image which has been labeled with attribute, and we have an animal expert tell me this class should have this attribute X, Y, and shouldn't have Z. That's the two conditions you have to have in order to perform attribute zero-shot learning. Okay, so if we present this formally, this is a illustration of the zero-shot learning problem. You have each image represented by a feature vector X, and during training, you have a set of images which has been labeled into different classes Y1 all the way to YK, right? And during testing, you are not interested in recognizing X into one of these known categories or these seen categories. You want to recognize X into one of these unseen categories. In a conventional supervised learning approach, this problem has no solution because you have never seen any example belong to these new classes. And the old class data wouldn't help you to recognize these new classes. However, with attribute-based zero-shot learning, we have a middle layer which we call it attribute. And these attributes basically act as a bridge between the level feature and the class label. And these attributes are shared by all the different classes. In the example I showed before, basically for all animals, you can summarize a list of attributes each animal should have or shouldn't have, yeah, which are relevant to animals. And you can then describe each animal classes using this set of attributes. In fact, there are animal experts who have summarized 69 attributes, which are sufficient to describe all the animals. And if you present this list of attributes to a human, the human are able to recognize new classes based on those attributes. And those are the attributes people use in computer vision algorithms based on attribute classification. So basic idea is that we have a middle layer, which we call attribute, and the training data now can be used to learn an attribute classifier for each one of them, which means giving a test data, X, I can predict the value of this attribute. Then for each unseen classes, I've got a description, we call it a prototype, which have a binary value either 1 or 0 regarding to this list of attributes. Then I compare the predicted attribute with the prototype attribute, and I will assign the class label to the new data according to how similar the predicted attribute list and the prototype attributes are. So that's the basic idea of attribute learning. So to summarize, if we have seen a zebra, and we see that it has stripes, it eats grass, and has tail, and has claws. This is zebra. I don't have many other images of this nature. And then I have a new image. I have never seen a lion before, but I know what a lion should have in terms of this attribute. Somebody told me that lion shouldn't have stripes, shouldn't eat grass, should eat meat, and should have tail and shouldn't have claws. If I learned what this attribute means, I could simply predict this is a lion. Yeah? The same idea can be applied actually to video data as well. For example, if I have some video which contain a birthday party, and I summarized to say that a birthday party normally feature candles, cakes, and people clapping, because after their birthday person blow the candle, typically people would clap their hand, and not very rarely involve some dance. You typically have a wedding dance, not a birthday dance. So these are the description or attribute list for a birthday party. And then I have a new class called wedding dance. I have no training example for wedding dance, but somebody told me a wedding dance typically do not have candles, shouldn't have cakes either, but should have people clapping their hands, and should have people dancing. Now with this, and I already know what do you mean by clapping hands in terms of the movement of the hands and in terms of the sound made by clapping hands, and what you mean by dancing also in terms of the body movement and the sort of music in the background. All these things considered, giving this prototype and giving a video which contains a wedding dance, I can recognize it. Yeah, so this is the basic idea of attribute learning. As I said, this has appeared for about 5 years ago, and it became very, very popular in the past 3 and 4 years. It's a very hot topic in computer vision. And there's some further papers. Okay, so this is the first part. I hope you have some idea of how people can do zero-shot learning based on attribute. What is the basic idea behind it? So now I will look at some recent work I did with Yan Fu, Tim Hospitals, and Shengdong here. So what I want to do is that I will first look at the limitations of existing zero-shot learning approaches based on attribute. And I will then introduce a solution to solve these limitations. Okay, so the conventional attribute learning approach, there are many different models, but one of the most popular ones is called DAP. The DAP stands for Direct Attribute Prediction. So what does a DAP mean? This is the graph I have shown before. So the idea is that I have some training data. These are my training data. This is the low-level feature. These are the attributes. So I use the training data to learn a projection between the low-level feature and the attribute space. You can imagine if you have 50 attributes, then you have a 50-dimensional space. And your low-level feature typically is in the order of thousands dimension. Then you learn a projection, which means you can predict, giving a low-level feature, how likely certain type of attribute is contained in that image. So you learn a projection between this low-level feature space and the attribute space, so that giving a new image where you extract the same type of feature, you can project it into the attribute space. Yeah? And for the unseen classes, the new classes, which you do not have any training data, you have a prototype, which are basically a binary vector, which tell you what kind of attribute should have and shouldn't have. So this prototype and your projection of the attribute are in the same space, which means you can measure the distance. So the DAP, the idea is that you project the unseen image feature into the attribute space, then you look at all the prototype of the new classes and assign this new image into the class which has the prototype closest to the projection. So that's the basic idea of DAP. So what is the problem with DAP, direct attribute prediction? We identify 3 problems, and for which I will give a more detailed explanation in the slides follows. So the first problem is projection domain shift problem. The second problem is prototype sparsity problem, and the third problem is the lack of ability to explore multiple semantic representations. Okay, so what do we mean by projection domain shift problem? Let's look at those animals again. Let's say we have one class called zebra, another class called pig. Yeah? So zebra are something we are very familiar with. Let's say we have a lot of training data. And the pig are something we want to recognize without seeing any images of pig. And we know that zebra has an attribute called has tail, which means all the zebra has tails. And the pig also has the same attribute. All the pigs also have tails. Yeah? The idea is that this, what tail looks like, should be learned from zebra and transferred to pig so that you can predict whether this image has a tail or not. Right? So what is the problem? The problem is that the tail for zebra and the tail for pig are very different visually. Yeah? The zebra tail are long and straight, and the pigtail is short and curly. That's the main difference. So let's say you learn a classify for tail from zebra, and you apply this classify to this new image. Yeah? You may not be able to predict correctly. This image also has a tail, because what tail looks like can be very different. Yeah? And add all these different attributes together, you will have a bigger problem. Let's say this is the zebra class, and this is the prototype for zebra, which means you have tail, live on grassland, and eat grass, and so on and so forth, has strips. Yeah? This is the prototype, and these are all the images I projected into the attribute space. You can see that pretty much the attribute is in the middle of the attribute prototype is in the middle of those data points. But if you project your pig image into the same space, using the projection I learned from other classes, and the prototype point will be miles away from the actual data points. So this is the prototype point for pig, and these are the actual data point for pig. How can you recognize those images as pig? They're so far away. So the reason is because all these attributes, what they look like, actually has some subtle differences. When you add these subtle differences together, you will have a big shift. And this shift is a problem people haven't identified before, so there's no solution for it. And we aim to propose a technique to solve this problem. Yeah? And our technique is called multi-view embedding space. You can see that after we do the embedding, this is the pig prototype, and these are the points corresponding to pig image. Now the prototype is in the middle of the points, so it's easier to recognize. Yeah, so this is the first problem. The second problem is called prototype sparsity problem. As we said before, for each class, we have a single prototype point. Yeah? And we have loads of data belongs to that class we want to recognize. So how can you recognize this point using this prototype? Because all the images of pig have different colors, captured from different camera angles. So visually they're different. The huge intra-class variations. And using a single prototype, which is single points, it's very difficult to recognize all these points. So we have a sparsity of the knowledge about pig. We only have a single description, which is not enough. Yeah? So that's the second problem. The third problem is that how can we explore multiple semantic representations? Okay, we so far only talked about attributes. Yeah? Attribute is one way to describe a new class. There are actually many other ways we can use to describe a class. For example, recently there's a very powerful model called semantic word vector space. Yeah? This is done by the Google people, and they have this model called word vector. So the idea is that I look at all the English sentences in all the English articles I can get my hands on internet. Yeah? And I build a language model. The language model is to see that if I say words, one word, what is the most likely words next to that word? Yeah? For example, I'm eating my lunch. So eating and lunch and eating and dinner, they are pretty much, in many cases appear in the same sentence and very close to each other, which means these two words are closely associated. Right? So what people do is that the linguistic people, the computational linguistic people, take all the English sentences and learn some sort of correlation model, which can be used to complete a sentence. If you speak two words, and this model can be used to finish the sentence. Yeah? So this is called a word language model. And a side effect of this is that every single English word now can be projected into a word space and become a high-dimensional feature vector. Yeah? For example, we found out this space, typically is 1,000 dimensional space, capture all the semantic relationships between different words. For example, if you have a word called king, and you have another word called queen, so what is the relationship between king and queen? They have similar job. The only difference is that one is man, another is woman, right? And in this space, we found out the vector for king minus the vector for man is equal to queen. So which means the language model actually captured what does a king mean and what does a queen mean and what is the difference between king and queen. So it's actually a very powerful model because it learned using so much data. We learned this model using 4.3 million Wikipedia pages, which basically covers pretty much everything we know about different things in the world. Yeah? So that's a very huge, powerful model we can use. So this model can be used to replace attribute. Basically, for each class, we can project this into this word space, and you have a vector representation. Yeah? And if you have a training set of images, like a cat, dog, you can learn a mapping between what the image feature look like and what a word vector look like. You can learn this mapping. Then you apply this mapping to new images. Then you look at how close this new image is to different classes. Similar idea as attribute. But this time, we don't need any more attribute to any more expert to tell us what does each class mean. We learned a language model from 4.3 million Wikipedia pages. We got everything we need. So which is basically means that it's free of any human labeling cost. It's completely learned from internet. Of course, Wikipedia page condense all the human knowledge about different categories, right? So they are very useful anyway. So what I would say is that we have many other semantic representations apart from attribute. How can we combine them together? Because they must contain some complementary information. So it's very desirable to combine them together. So that's the idea. So in terms of technical details, I do not have time today to discuss. I would refer you to our papers in these slides. I'm sure you will have access to the slides later. This diagram basically gives an overview of the idea. You have some images you want to recognize. In this case, it's panda and a pig, right? So you have some low-level features, typically in the order of thousands dimension. So they are represented in a high-dimensional feature space. From the feature space, I will project them into multiple semantic spaces, including attribute space and the words vector space I just mentioned. Yeah. So now you have another two views. Our idea to solve the projection domain shift problem is that we do a so-called transductive embedding, which means we look at these three views for the testing data, and we try to maximize the correlation of these three views so that they are forced to be correlated. The problem we had before is that the prototype and the feature projection are miles away. Now we say that let's correlate them together. Let's narrow down this gap. So that's our idea to solve their projection domain shift problem. So after we use these three views to learn embedding space based on the canonical correlation analysis, we can project all the points much closer in a so-called embedding space. Then in this embedding space, we build a graph and we do the label propagation. So this is related to what Felix just introduced. If you want to partition a lot of data into different classes, what you could do is to form a graph, then do a graph partitioning. And what we are doing here are related, but slightly different. What we do is that we still form a graph, we form a KNN graph. And each nodes actually have multiple views. Yeah? And we do a Bayesian average to combine them into a single graph. And we have prototype, which is a single point, which tells us which class this point is. Then we propagate this prototype to these unlabeled points via random work. And we want to find an optimal labeling for all the points. That's the basic story. Of course, there are some, this is a well-studied problem, label propagation on graph for clustering for classification. Yeah, so we just use existing technique with some improvement. And after that, you can see that the panda and the pig class are well separated after that. And we also have another extension based on so-called hypergraph, and I wouldn't bother you with the data. So what we can draw a conclusion is that this semantic word vector is very powerful. We train using all the English Wikipedia pages, 3 billion words, which basically is a treasure of knowledge we have. And our framework can take any number of semantic view, including the deep features, deCAP and overfit. So the deep learning has been a breakthrough in the past 2 or 3 years for not only computer vision, but also for speech recognition and all that. Deep features are very, very powerful, and of course this is not the focus of this talk, but what I want to say is that those deep features can be used easily in our framework, and they can be considered as somewhere between low-level feature and the semantic representation. So what we have, this is the early result we did without deep feature. This is the new result we have with deep feature. You can see that existing work for animal-rich attribute data set, 50 classes, 40 classes as training, and 10 classes as testing. So these 10 classes don't have any training sample, we want to recognize them. Existing work around 40 something, and now we get 80, which means without any training sample, I can recognize these 10 classes with 80% accuracy, so which is very promising. If we do 50 class birds, so this time we have 50 classes, but all of them are birds, a different type of bird. So it's very hard even for human to get 50% for 50 classes. Yeah. We also do at the moment we run an experiment for 21,000 classes. So you can see that the performance has been improved dramatically using this new model. This is an example of what has been learned by our model. Let's say we use the super duper overfit deep learning feature for these 10 new classes. They are a mess, right? So you can't, there's no chance you can separate these 10 classes. Even with the most powerful feature you can come up with so far. Yeah? We project this low-level feature into the attribute view and the word vector view. You see some promises. Yeah? So it's easier to separate them, but it's still very noisy. Yeah. Then now we do the embedding, this 3 view, plus some other views, other deep features. Then you can see that all of them are well separated. Yeah, of course, some of the classes are very similar. View and dolphin, they are still close together because visually they are similar. But you can see that they are much easier to be separated. That's why we get 80% recognition accuracy. Without any training sample, yeah, we can get 80% for these 10 classes. Okay, so these are the references, and okay, so to conclude, the computer vision research has moved on from a small, contrived environment-based recognition task to large-scale, in the wild experiment, which means all the data coming from, Flickr and YouTube, everybody just took it using their cameras, smartphones. How can we recognize different objects, different actions, different events? And how can we do it in large scale? Thousands of classes, millions of images and videos. And now people are interested in how do we transform the knowledge we have learned from some small number of classes where we have plenty of data to some new classes we do not have any data. And this work I present today basically show some initial achievement, let's say, in this area, but there's still a long way to go, right? How can we move on to these 21,000 classes? As Philip said, if we have 21,000 classes for the ImageNet data set, each class can have 1,000 images, which means we have about 20 million images. How can we build a graph on 20 million images? How can we do a label propagation on a lot of big data computation issues we need to solve? Okay, any questions?
Any questions? I have a question.
Yeah.
It's really interesting in recognition. I mean, you mentioned social media, because recently there's been an interest on how you can follow someone's social media and, for example, give advice saying you're living sites with heck because you're eating some burgers and stuff. And my colleague Hamid is working in the school and he's trying to identify from Twitter and these kind of, they're using hashtags to do that.
Yeah.
So do you think this kind of classification can work on food pictures, which is really hard to distinguish?
Yeah.
For example, a green salad from a green tea dessert. So can you tell the difference and so on?
Well, I think that's an interesting question. So what we have from social media is basically unlimited amount of information there. For example, if you want to recognize, if you want to distinguish these two types of stars, they look very similar, but there are some subtle things which separate.
Yeah. So
how can you do it? You do not have sufficient images for you to then classify, to find out which part actually set these two type of food apart. But what you can do is that you look at all the text descriptions.
Yeah.
Some people have left some message on the chat room. They evaluate a different type of food, and we properly emphasize certain things which really are the key attribute, let's say, which can separate these two things. Then you have a good starting point. If you know that's the difference between these two classes, then you can then search the internet, find some example of this particular images with this particular attribute. Then you use that to recognize these two classes. Yeah.
Somehow the working here, when you mentioned, because large database.
Yeah.
So it needs some kind of distributed and whatever Felix mentioned before, because access to this information and processing time.
Yeah.
So do you think this is something feasible in the future to have something like Google? Just put like, I know there is some Google search engine like image, but this doesn't work really good.
It's working pretty well and improving all the time. But obviously, there are still some limitations. But as I said, nowadays, because of the social media, we cannot complain. We don't have data. It's just a matter of how can we use this data, how can we mine the useful information, and that's still an unsolved problem. Yeah.
Also, it's really interesting here is what do you get the expert knowledge on what are the actual attributes and features. I was thinking, because you use Wikipedia, right, as the base data set. Are there any semantic web database, such as Freebase or so, that might be something a bit more structured? Would that be more useful than having to actually process?
Yes, for example, there is something called WordNet. So those linguistic people, they organize all the English words into a big hierarchical map. You can actually visualize this map. Basically, animal has this, different categories. Then, from this WordNet hierarchical structure, you could measure the distance between a dolphin and a whale. Obviously, they are pretty close to each other. Compare a dolphin to a zebra. Yeah. So this is an alternative way to utilize the linguistic knowledge people have accumulated over the years, and which obviously can fit into our framework to help us to recognize dolphin, without seeing any images. What I'm saying is that there are so many different forms of knowledge, but the important thing is that we need a framework which can combine all this information together and try to find the most complementary bit. Because they also have some overlapping information. The word space can also tell you dolphin and the whale are very close. But they have their own strengths and weaknesses. So how can we use them together? It's one of the innovation we have in this work. But this nowhere near enough, in my opinion. There's still a lot of work left to be done.
Do you think adding somehow geometric information for the attributes may help in recognition? I think, for example, dolphins, may have a similar shape, and you can match shapes of the dolphin to the shape of a whale, or to a human, and more or less you would have a larger separation between the possible classes.
Yes. In fact, some researchers actually are working on this subject, because if you think about attributes, some of the attributes correspond to body parts, right? Whether this animal has tails, claws. Some of the attributes correspond to some, especially those adjective type of attributes, correspond to color, texture, material. For example, a car typically made of metal. Metal has certain texture, can reflect light. That kind of thing. And some attributes are obviously associated with certain parts. This kind of information are out there in the human language models somewhere. If you read enough, you would actually, without seeing any cars, you would understand, okay, car view is somehow in the bottom of the car, and the number plates in the front and the back. This kind of information could be extracted from human linguistic knowledge bases. But for computer vision, there are some other problems, especially from the camera angle. What is bottom, what is up, what is front, what is left. Sometimes it's ambiguous. But yes, those type of spatial location information is important for people to disambiguate different type of attribute and different class of object.
Any other questions? So if not, let's thank Tony and all the speakers for this morning, Felix, Pablo, and Graham for interesting talks and really opening our eyes to lots of applications.